All right, well, thank you, Steve Lucas, for that amazing, energizing presentation. Let's keep the energy going with our next speaker, Antti Sunnari, who has more than 15 years of experience in diffractive and XR optics. He is the CEO and co-founder of Dispelix, the company who develops and delivers elegant and high-performance see-through waveguides that are used as transparent displays in XR. Under Antti's leadership, Dispelix has raised over $50 million in funding and gained recognition as a global technology leader in XR waveguides. In his talk, Engaging with Dispelix, from standard to fully customized XR waveguides, Antti will discuss how, together with Dispelix, you can realize your product visions from waveguide design to mass production. Please welcome Antti. Thank you.
Okay, hello everyone. Great to be here, honored to be here, and it's great to see that the event is going so big every year, year after year, and especially after the COVID. So my speech today is about engaging with Dispelix and our visions on the products and what we can deliver on this waveguide area. So just a nutshell about the Dispelix. So the company was founded 2015. We are a Finnish company located in Finland. We have fully owned subsidiaries in US and China. Today, we are totally 150 talented employees. And what I mean by that, we have about 60% PhDs in physics or mathematics. We are a highly innovative company, so currently we have 150 patents and 200 patent applications. So in the essence, Dispelix is a waveguide see-through display component company. So our mission here is to make really good waveguides for everyone, so that OEMs that are making the products can actually realize their vision of the product. And that's the mission, what we are doing. The technology that we are actually using in our waveguides, it's called surface relief gratings, meaning that we form these small nanostructures on top of glass. And light diffracts on those structures, and that's the way that we can actually transfer the image from a small projector in the temple to the user's field of view. We are known pioneers in this waveguide design, fabrication, especially for the single-layer waveguides. Use single-layer waveguides that are full-color operated. Our focus areas here are designing of the waveguide, making the proof of concept of the waveguide, manufacturing. We are a fabless company. We have partners on manufacturing. We do a lot of development on the metrology, how to measure these waveguides, how to define different things on the waveguides related to image quality. And we are focusing on applications that are near eye or head-up display. That's the sweet spot of our technology. Our vision in this area is that in order AR glasses to be actually mass adopted by consumers, they need to look like a normal glasses. That's like the only way that this market will actually happen. And that's the driving force on everything that we do in the company. If we think about what are the key points, key things that you need to have in your glasses, good-looking AR glasses, and how to actually define those, we find like three different categories that are social comfort, meaning aesthetics, how it looks like, eye contact, privacy kind of things, The third one is wearable comfort. You know, what is the weight, how they feel on you, all the balances, is it balanced? And the last one is the visual comfort, which is the usual like optic specification or display specification, like brightness, sharpness, color uniformities, eye box, a lot of different specification. But in order to make like a real good AR glasses, even in the waveguide company, you have to take account on different kind of design parameters that are really important. Using that guidance, we made Dispelix Selva waveguide that is delivering a good form factor and visual acceptance. So we really focused on those things when we designed what is the color balances, full color operation. We are a huge believer on that, not like any monochromatic waveguides. The sharpness of the image, how sharp the image needs to be. And we actually find out that when you increase the sharpness of the image, how sharp is the image, you don't need that much illumination. The image doesn't need to be that bright anymore because you can read it easily. This waveguide works on the monocular and binocular displays. And it's designed for LED-based projectors as DLP, LCOS, micro LED, and so on. Moving on, a couple of words, deep diving on social comfort, what we mean by that. So first of all is the aesthetics. It needs to be eyeglasses form factor, like that's the only way. So we have used to interact with people wearing glasses, and that's something that is acceptable. If we try to put something else there in the user's face, the social acceptance actually crashes. But it also means that if anyone who is wearing glasses, and if you check, those are not 90 degrees angles by 90 degrees angles, those glasses. So you have like a frame wrap, so the lenses both lenses are a little bit tilted, and you have pantoscopic tilt, so the waveguides actually tilt or the glasses tilt. So all of these things you have to take into account when you are making a waveguide for a consumer product. One thing also is the eye contact. When we are interacting with each other, even the glasses are on or off, or you get any message there, you have to be able to keep the eye contact or have the eye contact with the people that you are discussing. So that's a big challenge in this area, and we have made a lot of improvements in that area also. And of course, privacy. You don't want to get a message from your doctor, and people next to you or in front of you can read what the doctor sent to you. So that's really important also. Moving on wearable comfort. So what we mean by this? So eyeglasses are really compact, if you really look. They're really like small, designed small, and it's a huge challenge for the whole industry to pack everything in that form factor. You know, you need batteries, electronics, and everything, and still you need to have this good form factor. Okay, we cannot contribute on that one, but where we are contributing is the waveguide. So it's really thin. It's like an 0.8 millimeter in thickness. We take care that it actually fits in the glasses. The footprint is small enough to have in the glasses, and of course you need to be able to change the size of the waveguide, because not one glasses are not fit for everyone. So you need to have a different cutting shapes. It's about weight. So we are doing on a single layer, not multi-layer stack. So it's thinnest, but it's also the weight is the least in the market. Then the last one is balance. So what we mean on this, like, you don't want to have the projector on top of your eye here or on your nose, but it needs to be in the location where the frame naturally goes into glasses. And once again, that needs to be in that location to achieve a good-looking glasses. Of course, there is the eye relief. You need to have an eye relief because these waveguides are not correcting your eyesight, your prescription. So you need the relief, eye relief from the eye to have a room for corrective lens, and then for your eyelashes also. And of course, the large eye box is important because the interpupillar distance varies a lot from human to human, so it needs to accommodate all of those. The last one is the visual things. This is the usual optical parameters. So on a brightness, you need to be bright enough so that it works in outdoors and indoors. Okay, in outdoors, there might be like dimming film to increase the contrast because it's really hard to compete with sun. And we calculated it's really hard. So it's better to dim the lenses, like you normally use outside sunglasses. Okay, the sharpness, what we have achieved is actually a same resolution as human eye. So now it's about whoever makes the product using our waveguide to decide how many pixels per degree they want to have or how big resolution. Our waveguide can support that. Okay, iBox, I mentioned already for the IPD, but that's the key point why waveguides are used in AR glasses, to have a really big iBox to accommodate different IPD variations of humans in a very thin form factor. And of course, color uniformities and all of those are really important. So keeping all of this in mind, what we have developed, what we have taken like into account of human physiology and comforts on different things, we made a collaboration with a company called Waveguides here. So this is our joint reference design showing what the glasses could look like today. Okay, once again, we are both startups, so it's 3D printed, but you put a little bit of metal and everything, you can get it even better looking. So what was the point was to show it how the glasses look like, and then also use components that are available. So our waveguide is in the ramp-up phase on a manufacturing, in the volume manufacturing, and Waveguide technology use components that are available today. So that was about our thinking on the consumer AR glasses, what we need to take into account, and what is our product there, and what kind of reference designs we have done with a couple of partners. But then we can move from that, okay, what about there is companies that have a vision on making a headset for certain, is it the gaming, is it enterprise use, and what we can do there as Dispelix. So with that kind of customer space, we are doing custom engineering. So we can customize all the parameters of waveguide. We can use LED light source, laser light source, even light field light projectors. So what we have actually offered there, what we have developed during the years, we have researched and developed the waveguides and how we implement that in the customer cases. So one is the design experience. You know, you have the form factor design, how the lens looks like and all of that. You have the optical parameters, and these optical parameters we are using our software. It's a proprietary simulation software with graphical user interface. We just implemented AI there, but it's not only AI, there's a conventional algorithms also. If we look a little bit closer what there is, so we can use linear and doubly periodic gratings with all the possible propagation directions. We moved from ray tracing technology to field propagation with the phase and polarization and all of those included. And that means that we are always 20,000 times faster than any ray tracing software. The heart is in surface relief gratings, so and diffraction. So because it's mainly on a diffractive, we can also design volume holographic gratings. Double-sided multiplate systems, done that. We optimize the MTF, and we do the tolerancing also in a software, which is really important in the manufacturing aspect, and it runs on high-performance clusters. Then throughout the years, we have done not only the software development, we have tested hundreds, if not thousands, of materials. We do little bit material development. We have developed different architectures and different geometries of the waveguides. We have built a manufacturing process that we are currently working on with AAC technologies and applied materials. And of course, metrology, it's a big part. On manufacturing end, our approach is dry etching. So we actually etch our structures in an active layer on top of the waveguide. And that's the same process that it's currently in use in semiconductor industry. Why we selected that way? There is more process steps than nanoimprinting lithography. And the reason is that all the tools are really mature. All the tools are really fast because they have been developed to be really fast. We can make better waveguides, of course, that's one thing. And one thing is the reliability. So we have passed all the consumer electronics like reliability testing, and we are currently moving on for defense sector reliability testing. And with that said, I'm going to have a couple of case studies what we have done on a custom engineering. So comfort and immersion. This was a project we did together with Waveguides, and Waveguides have the light field technology and the light field projector. And we wanted to get that one working on the waveguides to have a better form factor of the device. So after we locked down all the specifications and what we are doing together, the waveguide architecture and the waveguide design took us 6 weeks. After that, manufacturing of the proof of concept sample was 18 weeks, and metrology took 2 weeks. And now once again, we had to build on the metrology and come up how this is measured. Another one is on the field of view. So we have a customer that says that we want to see our product needs plus 90 degrees field of view. And that was a big challenge for us. So no one have made a waveguide on over 90 degrees field of view in any device. So this was a little bit longer project. So first we had to come up with the architecture which can support that large field of view in a waveguide. And that took us 2 months and really nice patent on waveguides. After that, we had to develop our software because we have never done that kind of field of views in a waveguide. We have to develop our software, 2D gradings, and the optimization, and that took us 6 months. And then we made the proof of concept, and once again you have to develop every time your manufacturing process because you are doing different size and different features and everything. And this was a multi-layer solution for one eye, and that took us 4 months. And then we had to build metrology. There is no tools to measure that kind of field of view in a waveguides. So we have to develop that and come up how we use these standard tools to measure jigs and everything, and that took us 2 months. And of course, every time there is these interdependencies on everything. So first of all, when you increase the brightness of the system, battery life will always go down because you pump more energy in the projector. Also, that means that you easily have a thermal management issues. And one way to fix brightness or get higher brightness is to decrease the field of view because the same image is spread in a smaller area. If we think about the field of view, when we increase the field of view from 30 degrees, 40 degrees to 90 degrees, it means that the eye relief goes down and also the eye box. Change in the eye relief actually changes a lot wearable comfort because you have to go like more in to see the whole image. So you have to, in that distance that the glasses are, you have to see the whole image. And of course the eye box, if you move your eye and the image, you lose the image. That's a big problem. These are I'm proud of our partnership and a partnership network. So we have from manufacturing, glass materials, metrology, projectors, and different areas on this. Just to finalize, so tomorrow we have a booth for 12. Come and see it. We have the demos there for everyone to see. Right. Thank you all.